Before anything, let me tell you a story. This picture was shot for the movie Cleopatra, but it didn't make the cut. Still, I believe I know what this scene is about, and I recognize some historical references, including to a dinner party that had a profound impact in human history. So let's see. The plot is this. They are in Alexandria, 48 BCE. In the middle, we have Sosigenes, a Greek astronomer to whom we owe a great deal. I will talk more about his work later, but in this movie, he's the most trustful advisor to Cleopatra. And at that time, Cleopatra was having a power struggle against her brother, and she desperately needs Caesar's help to resolve the situation. Julius Caesar, the Roman dictator, then became Cleopatra's lover and made her Queen of Egypt. So, to celebrate her ascension to the throne, Cleopatra in real life, not in the movie, in real life, threw this lavish dinner party described by Roman poet Lucan in his book Pharsalia. And Lucan tells us this. The room was the size of a temple. It was filled with a wonderful smell of exquisite food. Not only delicious, the food was colorful, with exotic birds and fruits served in golden platters, the water in crystal ewers, and the wine in jeweled goblets. Lucan also says that Cleopatra was dressed to impress. But, despite all the temptations in the room, what really caught Caesar's attention that night was an old wise man by the name of Acoreus. Not Sosigenes, but perhaps there is a reference here, because Acoreus talked a long time about astronomy, the floods of the Nile, and the relation between those two and the Egyptian calendar. That might have been an aha moment for Caesar. Look at his face. So that when he returned to Rome, he hired Sosigenes to lead the much needed reform of the very messy Roman calendar. And that finished the first story of my presentation. So thanks everyone for attending or for watching the video recording. I am Cassio Neri. I'm a PhD in mathematics, former professor at university, but currently I work in finance in London. This is a research collaboration with Professor Laurent Schneider of EM Lyon. EM Lyon is a highly rated business school in Lyon, France. And it has been published under a Creative Commons license, which is great, so you can freely download it from the internet. But I also brought a few copies here for you. Please help yourselves. So it has been published by Wiley Software Practice and Experience. My part of this work was carried out in my spare time, has nothing to do with my current or previous employers. I'm here in a personal capacity, and all the opinions that I'm going to express are mine and do not necessarily reflect that of my employer. Okay, good. So I'm going to cover 4 algorithms. And despite that my name is Cassio, I won't talk much about time. I certainly will, but I'll talk most about dates or calendar algorithms. And along the way, I'll touch upon decisions taken hundreds or even thousands of years ago that deeply impact the performance of these algorithms on very modern CPUs. Okay? As I said, I won't talk much about time. It has been covered by Ben's presentation yesterday. Thanks, Ben, for coming, for being here. It was a wonderful presentation. If you missed Ben's presentation, I strongly recommend you to check it out as soon as the video comes out. And if you did attend Ben's presentation, I strongly recommend you to watch the video as soon as it comes out. It was really cool, full of math, history, algorithms, C++, enjoyable anecdotes, and etc. Actually, if C++Con was, C++Now was a video streaming company, speeding date will be season 2 of calendrical C++. Okay, so I hope you enjoy season 2 as much as I enjoyed season 1. Thanks, Ben, it was a great talk. So let's start. As I said, I'm going to cover 4 algorithms. None of them is the date of Easter. Please watch Ben's presentation. You must. And we are going to spend more time with the most complex of these 4 algorithms, which is the following. Digital devices, including my humble Casio watch, display date and time in fields like this, like we are used to. But that's not how these devices keep track of time. Let's take a closer look. Usually, they keep a counter of ticks since some point in time. For instance, this slide is counting seconds since January the 1st, 1970, the so-called Unix epoch, as said by Ken Thompson, Dennis Rich, and other creators of Unix. The Unix epoch is also used by stud chrono system clock, but other systems might use other epochs, or also the resolution of the tick might change. So the question is this: how do we convert seconds or ticks to dates and time? For the time part, it's easy. Involves just a bunch of divisions and modulus operations and working states, where in each state we get the value of a field and the input for the next state. And what makes that problem easy is the constants of durations. Minutes have 6 seconds, hours have 6 minutes, and days have 24 hours. And also, weeks have 7 days. But this pattern breaks when we get to the date part, because the number of days in a month or in a year is variable. So the main problem we wish to solve, and we are going to spend more time on this one, is that given the number of days since some epoch, find the date. Of course, Lawrence and I were not the first to solve this problem. So let me show you one solution, that of .NET 6. Don't bother trying to read the code, but please notice the slow moving parts. Can you see it? I hope you can see it, okay? So I'm showing this code just to point out some coding constructs that harm its performance. So we have branches and we have loops, okay? This code also has 2 lookup tables, and it is true that lookup tables like this one might help the performance of this code when the L1 cache is hot. However, the cache is a precious and fairly limited resource. So this code is competing for cache with other running pieces of software. So it's really hard to tell, but it's a real possibility that the overall performance of your application degrades because of cache thrashing. And here is our solution. Again, never mind if you cannot read the code, we are going to see that in details, okay? But I want just to tell you now that it contains no loops, no branches, no lookup tables. It's entirely arithmetic and involves just a bunch of divisions and modulus operations, and is organized in stages, where in each stage we get one field and the input for the next stage. So it's very similar to what we do for time. And that's not a coincidence, okay? Indeed, we are going to see a mathematical setting under which the 2 problems, the date problem and the time problem, can be solved in the exact same way. It just happens that for the time part, there are some operations like division by 1 that are simplified, they are just not there when you put in the code, but conceptually they are there. And since I'm talking about performance, let's show some measurements. But if I tell you that our code runs in 5 nanoseconds, that doesn't mean much, right? 5 nanoseconds is a very short period of time and is unreachable to our senses. And I want you to feel it. So this animation rescales time as if our code takes 5 seconds to run. Let's see how long other takes. Please bear with me. Finally, I hope this is the most boring part of my talk and the entire conference, okay? So let me elaborate a bit further and show some systems that use these hours. As you can see, ours is in chrono that comes with GCC, libstdc, and also in the Linux kernel, I implement both myself in C++ and C and contributed. Then Sergei Pavlov read our paper and implementing C#, and he contributed that to .NET 7. So the implementation I showed 2 minutes ago, whose time you can see here, is now obsolete, okay? And when .NET 7 was released, some Microsoft engineers made a measurement of performance improvement in .NET 7 compared to .NET 6, and the measurement is very much aligned with ours. So it was independently verified. I'm not lying to you, unless you may think that I pay a huge amount of money to Microsoft to lie. So, yeah, I wish. So, given that, that is the motivation to try to understand our algorithm. But now let me give you an overview of this talk and its 3 pillars. First, we are going to continue the journey on the history that Ben started and is amazing. So we are going to cover the history of the Julian and the Gregorian calendar. My main reference is the classic book Saturnalia by Macrobius. There are other classics like Ovid, Plutarch, and Censorinus. Unfortunately, they are slightly different in their accounts, so there is a lot of debates among historians what really happened. So when I found some divergence, I stick to the account by Macrobius. Then we are moving to the maths, and we are going to introduce this mathematical setting under which the date problem and the time problem can be solved in the same way, and involves integer functions of that form, okay? So note the division. If that division was usual division between integer, meaning rational divisions, then f would be said to be an affine function, right? But in that presentation, forward slash denotes Euclidean division. We can think like C++ C integer division for positive operands, okay? And because this is Euclidean division, Loris and I call this type of function an Euclidean affine function. And then I'm going to show you some results. And then we are going to apply these results to code. And we are going to see some transformations in code that largely improve the performance of our algorithms. So let's start with the origin of the calendars. So we all learn in school that days and years are a consequence of Earth's motion, but our ancestors, they did not know about that, but they could clearly grasp days and years. So they built impressive monuments to keep track of solstices and equinoxes. Probably the most famous of all is Stonehenge in England, but apparently Woodward in Australia is the oldest, 13,000 years ago. But then later, our ancestors, they developed calendars to keep track of days, months, and years. And talk about months, and also the moon. What happened is the moon revolution around Earth creates the moon phases. And a complete cycle is conceptually a month. And actually, as far as the design of ancient calendar is concerned, the moon was the most important celestial body. Might not be obvious to us because we have a lot of electric lights around, not here in Aspen when we leave the conference, but for our ancestors, a full moon allowed them to have some night activities that were otherwise difficult or impossible. So they paid close attention to the moon, and for that reason, many ancient calendars are purely lunar, like the Muslim calendar, or lunisolar, like the Chinese, and the Jewish, I think, is also a lunisolar calendar. But the Romans, at some point, they gave up any attempt to align months to days and years. So that's why I removed the moon from my picture, and I'm not going to talk much about the moon anymore. And why did they do that? Because it's a very hard problem. Actually, just align days and years is already very hard. Oh, okay, back to months, sorry. They kept months in our calendar just for historical reasons, but it completely lost its astronomical meaning, okay? So now, why did they give up on the moon, on the months? Because it's hard, and just align days and years is already very hard. Let's see why. If you want to design a calendar, somehow we have to face this problem here. Find two integer numbers, positive integer numbers, n and m, such that n times the duration of the year equals m times the duration of the day. And so the ratio between the two durations must be equal to the ratio between the integers, and as such must be a rational number. But in reality, this ratio is not rational, so this problem has no solution. Worse, this ratio is constantly changed, and changes about in the 6 digits after the dot in 100 years. So it's very slight change, but it's changing. And okay, it's a problem with no solution. But even if you cannot get the real number, we can get a rational approximation that is good enough, that is close enough. And in essence, when people talk about the precision of a calendar, in essence, what they mean is the quality of this approximation, okay? We are going to see a few of those approximations later on. Okay, so that's how we started needing calendars, and we try to build calendars. Now, let's see how the Julian and Gregorian calendars came about. Okay. Romulus, the founder and first king of Rome, is credited for this calendar. Notice that the months, they have familiar names, and some even spell the same in English and Latin. Here I wrote in Latin. Except for quintilis and sextilis, which are a bit strange. But from quintilis, the 5th month onwards, the months were named after their position. Quintilis means the 5th month. Sextilis, the 6th month. September, the 7th month. That makes much more sense back then than it does today, right? What doesn't make sense in this calendar, it had just 10 months. And those 10 months account for 304 days. The remaining days were part of winter. But since winter was a period of low activity, Romulus didn't bother to split that in 2 months. And here's a crazy thing. The duration of the year was not prescribed. It was decided by the pontifices, the high priests of Rome. And it worked like that. On the first day of each month, the pontifices would call the Roman citizens to the streets to announce the new month, the beginning of a new month, and the activities for that month. And in particular, the call for Martius would be the beginning of the year and the end of winter. And as I said, they would call the citizens to the streets. The Latin word for call is calari, and for this reason, the first day of the month was said to be the calend, and there was the calends, the nones, and the ides. Please watch Ben's presentation to know more about the calends, the ides, and the nones. And so it's really crazy that it's a decision, and that decision was supposed to happen around the North Hemisphere spring equinox, to keep the calendar aligned with the seasons. But from the algorithm point of view, that's just impossible to write an algorithm for that, right? It depends on the decision of the pontiffs, what they want. But then came Numa, the second king, and he split winter into Januarius, Februarius. He made Januarius the first month, and he changed a little bit the number of days in the months. In Februarius, the last month, usually had 28 days, but every now and then it will get extra days, so it could have 50 or 51. So the year could be 355, 377, or 378 days. There was a rule telling the duration of each year. But it was quite difficult for the people at that time. It involved division by 24, modulus 24. It was too complicated. So the pontiffs decide to ignore this rule, and they still decide the length of the year as they pleased. Then the Decemviri moved Februarius. The Decemviri was a commission of 10 men who wrote the first Roman code of law. And they had some political and military reasons to move Februarius, but from the algorithm point of view, it was a big mistake. And we are going to see why and how to deal with that. And here is another crazy thing. Rome at that time was a republic, and the government lasts for 1 year. Since the pontiffs decide the duration of the year, they decide the duration of the government. So either by ideology or pure bribery, they abuse their power. And at some point, the calendar got completely out of sync with the seasons. And that's the mess that Julius Caesar set himself to solve. And as I told you, he hired Sosigenes, who came up with this calendar, which is very similar to ours. That's why I told you that owe a great deal to Sosigenes. It was his idea. So Februarius usually had 28 days, but every 4th year, it will get an extra day. That's the leap year rule, okay? And so 3 out of 4 years, they would have 365 days, and the 4th year would have 366. So the average duration of the Julian year, calendar year, would be 365 days and a quarter of a day, which is a rational approximation to the real number that I recall in the balloon. But then the pontiffs screw it up again. As Ben explained, they have a strange way of counting days, so they misunderstood that. They thought they should include a leap year every 3rd year instead of every 4th. So a few years later, the calendar got out of sync with the seasons again. So then the Senate and Augustus Caesar, the first emperor of Rome, they first renamed Quintilius and Sextilis to Julius and Augustus in honor of Julius Caesar and Augustus himself. They stopped leap years for a while until the calendar got back in sync with the seasons, and afterwards the leap year rule was correctly applied. But despite these small adjustments during Augustus Caesar's reign, this calendar is called the Julian calendar. So the error of the average duration of the year is about 11 minutes. It doesn't seem much, but it amounts for a full day every 132 years. So after 16 centuries, the error was quite noticeable. That's why the Pope Gregorius XIII commissioned a reform, and that reform was led by Christopher Clavius, but the main ideas came from Aloysius Lilius. And it was this. So Aloysius Lilius decided to target an average duration of the year, this number here, 365.2425. And I recall in the balloon, the real number. And it's possible to get closer. And there are some calendars that do that, like the Iranian calendar. But there are some aspects of Lilius' proposal that, in my opinion, make it brilliant. Let's see. First, he looked at as a correction of the previous rule, the Julian leap year rule. So he took the previous average year, subtract 0.01, and add 0.0025. Then you get the Gregorian average year. And these two numbers, these two corrections, can be conveniently written as 1 over 100 and 1 over 400. And that allows that new rule to be very clearly expressed in words as a revision of the old rule. And it's, in plain words, is like that. A leap year is one that is multiple of 4, exactly as it used to be, and the extra for new rule, except those that are multiple of 100, but not 400. And knowing if a number is multiple of 100 and 400 is much easier than if it's 33 or not 33, and what is the modulus 33 like other calendars do. So it was much simpler. And notice that 3 out of 4 centennial years, the 2 different rules will diverge. Only 3 out of 4 centennial years. And the first such year after the reform was 1600, which is also multiple of 400. So it's the exception to the exception. So people alive in 1600, they did not see any difference between the 2 rules. The first time they really diverged was 1700, 118 years after the reform. So people had plenty of time to adapt, like our bosses, right? So they give you that deadline such deadline to us, right? So they have plenty of time to adapt, and for me this is brilliant. I love the simplicity of the rule and Linux forward-looking. So, especially because changing a calendar is not an easy task. So let me show some confusion that adoptions of new calendar bring. So for the Julian calendar, it was adapted in 45 BC. So the previous year, 46 BCE, need to have 445 days just for the new calendar to start fresh, aligned with the seasons. Okay? And that year entered history annus confusionis ultimus, or the last year of confusion. For the Gregorian calendar, most Catholic counters, or some Catholic countries, adopted it in 1582, just after the reform. But again, because of the accumulation of the error in the Julian calendar, to put back in sync with the seasons, they have to skip 10 days in October. So the 4th of October was followed by 15. In Britain, the change happened in 1752. The law here was passed in 1750, but the calendar is starting in 1752. And for the same reason, to keep aligned and to align with other countries that were already on the Gregorian calendar, they have to skip 11 days in September. And actually, Linux users, you might have this command line program call, and you can ask for September 1752 calendar, and you are going to see this jump. It's not a bug. It is what it is. But that is historically accurate from the perspective of Britain, some parts of the US. For instance, Louisiana was French territory. So it had moved to the Gregorian calendar much earlier. Alaska, on the other hand, was part of Russia. It didn't change calendar at that time. It was much later. So imagine if you have to write a program that is historically accurate in every geography. That's impossible. Would connect to the GPS, to the internet to know where you are, the history before to find the date. It would be a nightmare. So pragmatically, that's the only exception that I know, but pragmatically what we do is we implement the so-called proleptic Gregorian calendar, which takes our calendar that we have today and extrapolates to every date in the future and every date in the past. And that finished my crash course on the history of the calendar. There are plenty more in Ben's talk, so I cannot say enough. So please watch his presentation, there's much there. I could spend hours talking about that, and I'm sure Ben understands what I'm saying. But this is a C++ conference, and you are here, you want to see C++ code, algorithms, and etc. So let's bring it on. This is from the GCC's manual. And I love this code, and I myself one of these programmers. So let's try not to be. So let's start with a very simple algorithm. Is it why a leap year? That's the thing that differentiates the Julian and the Gregorian calendar. And virtually everywhere I looked, that's the implementation, okay? And just to simplify a little bit, so we use logical operations, so there are short circuiting, but let me just express the same logic, but with ifs. It's easier to to analyze. Has anyone here came across this implementation, this logic before, and knows what is the argument for this logic? Anyone knows the argument for this logic? No? Okay. So they say, the people who advocate for this logic, they say, in 75% of the case, we return earlier. So we don't have to carry out with needless calculations. In 27.5%, we just do one single divisibility check. But that's what I implement for GCC. I implement this one, which always does 2 divisibility checks. So for some, that might be optimization, but that's not what my measurement showed. My measure showed that my code was close to 3 times faster than the classical one. I'm not saying 3%, I'm saying 3 times faster. I was surprised. I was not expecting that, okay? So how can we explain such difference? Any guesses?
Fewer branches.
Exactly. Fewer branches, and on top of that, look at my branch. It's just one branch, and here we have 2. And my branch splits the path, the execution in 2 paths, one with 99% probability and one with 1% probability. The branch predictor is really happy with that code. I make the branch predictor's life much easier. It can do a much better job, and we get better performance. But we didn't stop there. I did also this change here. I didn't like the 400, I put 16. And that's not a bug. That's not a bug, don't worry. I leave it for you to prove that if we know, look, we only execute that part here when we know that y is multiple of 100, okay? And I leave for you to prove that if y is multiple of 100, then it is multiple of 400 if and only if it is multiple of 16, which is a power of 2, which is much better for the CPU, for the compiler, to generate code to see if it's multiple of 16 or not. Unfortunately, no compiler could figure that out. I have to do it manually. We didn't stop there. Ulrich Draper then, during code review, said, why not use the ternary operator just to select the second divisor? So the first one is 100. The second one is 4 or 16. Why not use the ternary operator to select the second divisor? So that's the idea. And then, okay, so the second divisor, D, is going to be a power of 2. And we all heard compilers very clever, and then we replace that with AND bitwise trick, very cheap AND bitwise trick, then you evaluate the expression, right? Not in that case. Some compilers even use a div instruction for that, which kills the performance. Okay, so we have to do it manually ourselves. So that's the essence of the implementation that I put in GCC. I did further optimization around the divisibility by 100, but that's another story.
Does it ever use a conditional move?
Exactly. Because of that, this code here, the major compilers generate using the CMove, so they generate branch-free, efficient code. That's branch-free. Wonderful. Very, very fast. Much faster than the classical implementation.
Why is this branch free? Because ternary operator is there, so it is...
Yes, but what happens is, so you have 4 and 16 in 2 different registers. And then it evaluates that expression and then decides if it has to move, say one register has 4 and the other one has 16. So the condition move says, depending on the result of this evaluation here, move or do not move. But it's not a branch saying jump to that place where I move or jump to that place. So for the CPU doesn't see the branch instructions. It just see a conditional move and the instruction after the conditional move. So for the pipeline, it can do all the stuff without having to guess which part of a branch it would go. So that's why CMove is much better than branching, And actually here, the branch predictor is not used at all. Leave the branch predictor to do other stuff. Help you other places that it might be needed. Not here. We don't need the branch predictor anymore. Okay, so second algorithm. So one gone, that's the second one, I guess.
Yeah, but what was the speed up?
It's closer to 3 times.
Also, it's in total.
In total, yes. In total, yes. But with the previous implementation, that one here, we get 2.6 times. And then we go more and more and more, and then we get 3 times faster than the classical implementation. Okay, second algorithm, or the classical. Last day of the month. So M is the number of the month. February is the ugly duckling of the month, so it needs to be treated separately, and it needs to know if the year is leap or not. So imagine all classical implementation use also the classical implementation of leap year. If we just replace the is leap year implementation with ours, we are already helping the classical implementation. But I want to pay attention to the second part, the other months. Usually there is a lookup table. And as we said, lookup tables, they compete for cache with other running piece of software. And I have to talk about safety, right? If M is not between 1 and 12, we have an out of access to the array, undefined behavior, security problems, and all that stuff we have been discussing the last few days. Here is my implementation. February, same stuff. The orders, this thing here. And when I submit that to GCC, I said, oh, that will be a tough call, will be a tough sell. But they bought it immediately. Actually, the first comment I have was, I like it, thank you. So it's cryptic. And I will not explain for you. I leave you the fun to understand what's going on. It's fun, I promise you, it's really fun. We can discuss later here. But in my original code, in here, I have an extra end with 1. But doing code review, Dr. Matthias Kretz realized that this was not necessary. The end with 1 was not necessary. And then we removed that. And it was not necessary because a very fortunate fact about the binary expansion of 30 is like the heavens, they want it to work, okay? We always thought the heavens are against us in calendrical stuff. In that case, they just want it to work, okay? And does work. And I'll let you to prove that does work. But pay attention also, another thing. I'm not competing for cache with other running piece of software. I'm helping elsewhere. And there is no undefined behavior here. Of course, M being between 1 and 12 is a precondition. But if you violate that precondition, I return to you a number that is meaningless, but I don't involve in any undefined behavior. There is no security problem in this piece of code. Another advantage. And the performance, I thought would be difficult because when we put these in a micro benchmark measurement, so we put in this loop and we try that 1,000 or millions of times, and then the cache becomes very hot and it's very efficient. And I said, if mine is not that efficient, I would have to explain, no, but the cache in a real situation is not really like that, so we are biased, so the measurement biased towards this one, but fortunately that one was like 10%. I would not brag much about that increase in performance, but it was 10% faster than this one. So I said, okay, I don't have to do the salesman talk. Okay? There is an alternative, which is this one. And performance-wise, there is not much difference between these two. About the same. But what I like in this one is that we see here that expression, 9 times n divided by 8, which is an Euclidean affine function. It's the first Euclidean affine function of this talk, not the first Euclidean affine function of this conference. There was plenty in Ben's talk, in the algorithm for the date of Easter. And I think I saw another one in another talk, I can remember now. So it's time for us to try to understand what is the Euclidean affine functions and its properties, okay? So we are now up for, yes?
Yeah, I'm curious. Did you have some method to arrive to this formula? Or were you just enumerating some binary operations?
This one here was just looking at the binary, trying to find a pattern, old way, natural intelligence, not artificial intelligence, try to find a match, a pattern. I found the pattern, and then I just expressed in bits, in bitwise operations. And then later, look at the bitwise operation. Oh, okay, I see, that's an Euclidean affine function. Then I got to that one. Okay, but it's true, it was not a very systematic methodology and etc. It was lucky.
Why is the alternative not slower than the R's version? Because R's uses...
No, these two are very, very similar. And that one is like, these two are 10%, about 10% faster than that one. But that might vary depending on the architecture, on the platform. That's my measurement. So if you want, please go and measure yourself. But between those two, the difference is in the noise. I will not say that this is faster than that one.
Why? Because we have multiplication and division, which are comparatively costly operations.
Yes, but the thing is, 9 is 8 plus 1. And there is a trick that the compilers do. They actually do a multiplication by 8, which is cheaper, very cheap, and add to 1. And actually, there is one instruction that does the whole thing. Is a hack that the compilers do. They use the LEA instruction that can do the two operations together. Okay? So that's, but there is not much difference between these two. Okay, so now we are up for some cool maths. And we are going to go back. So we have two algorithms covered. I explained the main one. We are going back to the main one now. And we are going to solve it on yet another calendar. Not the Julian calendar, not the Gregorian calendar, the Egyptian calendar. That's the calendar that Aquarius explained to Julius Caesar and gave Julius Caesar the idea, wow, maybe I should do something like that for the Roman calendar. So the Egyptian calendar was very simple. It had 365 days, period. No leap year involved, okay? So consider the dates the date that it's any days after the first year of year 0. So the first year of year 0 will be our epoch in that slide. So we want to find first the year. So I'm going to introduce three functions here. Y of n gives the year y. Y circ of n gives the day of the year, ny. And y star of capital Y gives the number of days before year y, from 0 to y. Okay? And pay attention to the colors because I'm going to use this color consistently for these functions and its relatives, their relatives. But I'll keep calling the functions by their name for the benefit of those who perceive colors differently, okay? So, because the calendar, every year had 365 days, is similar to time. So I probably have already figured out the formula for these three functions. Very simple. But let's forget the formula for a little bit, and let's try to understand the relation between these three functions graphically. So, two axes. On the x-axis, we are going to put the number of days since epoch. So 0 represents the epoch. And n is a point on that axis. Okay? On the y-axis, we put the year y. And it's clear that it's not only this particular value of n that yields the same y, right? There are 365 values of n that yields the same value. So actually the function y, the green one, is a step function. And the length of each step is 365. Now, by definition, there are y star of capital Y days before year y. So y star of y corresponds to the beginning of year y. Okay, that's how we place that in this graph. And by definition, the day of the year is the difference between n and the beginning of the year. It's the number of days from the beginning of the year to the date. So y star of n is that difference here, right? But if you do a similar analysis, but within a year, not from the beginning of, from the epoch, but within a year, here, if you do an analysis here, basically everything I said for years also apply to months. Let's take a closer look. The Egyptian calendar have 12 months of 30 days each. Not 31, 30, no. All the 12 months had 30 days. And the remaining 5 days of the year, because 12 times 30 is 360, so the 5 remaining days was not in a month. They didn't call a month. They call a period called epagomenal days. But we don't need to care about that. We can think that these 5 last days was in a 13 fictitious month. All we care about is finding a number between 0 and 12 that represents the month or the epagomenal years where each day falls on. And it's a very similar situation. We have 3 functions, m of ny that gives the month, m circ of ny that gives the day of the month, or simply day, d, and m star of capital M that gives the number of days before the month m, since the beginning of the year. And the relation between them is exactly the same as in the previous chart, okay? There is no fundamental difference. The main difference here is the steps are now 30, and 0 now doesn't represent the epoch, but the beginning of the year, right? And again, because the real months have 30 days, you might have already figured out these 3 formulas here. Do you see anything strange here? The number 5 doesn't appear anywhere. Those 3 formulas, they completely ignore the duration of the last fictitious month. And that's correct. That's interesting, and that's correct. Remember I said that the chamber made a big mistake because February is only complicated because it's not the last month. This thing here tells us that being the last helps. It works like this. Look at the definition of m star. It's the number of days before month m. So it doesn't take into account the number of days in the month m, only before m. So if the month is the last, it will never be accounted for because we cannot apply after that month. It doesn't make sense by definition of last. So February is only complicated because it's not the last month. And we can blame the chamber for that, but we are going to deal with that. So these formulas are also correct for the last month. Now I want to generalize this a little bit, right? We see a pattern. We did something for years, and the same pattern appears for the months. So let's generalize and say a period. A period here means a year, a month, or other type of period, okay? And again, we have this problem. Suppose that any days have passed since the first day of the first period. So again, first day of first period, I mean first day of first year, or the first day of the first month of the year, or something else, the first day of the first period, whatever period is in the context we are analyzing. So again, we have 3 functions. F of n gives the period q, f circ of n gives the day of the period, and f star of q gives the number of days before period q. The chart exactly the same as before. The only difference here is now they're going to allow the steps to be variable, okay? In the 2 previous cases, the length of this step for the year, the Egyptian calendar, was 365. For the month was 30, always 30, and now we are going to allow this to be variable. Let's see what we can do with that. So, the relation between these 3 functions in the general case are very well illustrated by this chart. And that's enough for us, for this presentation, to understand what's going on. But we can also express by these two equations here. But don't bother about the equation. Put here for completeness. In the paper, for the proofs of all the theorems, that's what we use. That's how we manipulate these things. But for the mental model, that chart is enough. Okay? So let's see what we can do with that for the Julian calendar. And I recall here the leap year rule for the Julian calendar. And now, the function that gives the year, the steps can be 365 or 366. Okay? So a reasonable attempt to get the formula, let's try to get the formula y star of capital Y, which I remember counts the number of days before year Y. So a reasonable attempt is this. I multiply Y by 365 as if all the years have 365 days, and then I make a correction that accounts for 1 day every 4 years, an extra day every 4 years. And we get this final expression here. Two bad news. That's not a multiplication, as it was in the case of the time and as it was in the case of the Egyptian calendar. So the things are a bit more complicated, but they don't need to be much more complicated, just a little bit. But the worst news is that it's wrong. It's wrong. This formula is wrong. It doesn't obey the leap year rule. So in that table, I'm tabling the values of y star for y between 0 and 4. And the difference between two consecutive values of y star is supposed to give the number of days in each year. So, but for 0, it gives 365. But 0 is multiple of 4, should be a leap year, and should have 366. So this is wrong. And for year 3, it gives 366. But 3 is not a leap year, so this is wrong. But we are off by 1. If you think a little bit, we are off by 1. That will be okay. That will be correct if the leap year rule was stated like that. But that's not the reality, okay? That's not how the Julian calendar works. So we have to do something. The fix simple. That's the correct formula, and you can figure out that this is a correct formula. But it works, but we can do better. We can do better. We are not going to use this formula. Bear with me. We are going to see later why we can do better, okay? And it's important now to, yes. Notice two things here. Okay, although this is wrong for the Julian calendar, this is, but we are not going to use, pay attention to the two expressions for y star. Both of them are Euclidean affine functions. So now it's time for us to try to understand the relation between Euclidean affine functions. So in the general case, an Euclidean affine functions take that form. In the particular case where a equals to 1 and b equals to 0, we get this formula here, and we know the expressions for f circ and f star. Like we do for times and for the Egyptian calendar, that's all we need. But for the Julian calendar, we need something like that. But what is the expression for these two? So that's the missing link. We have to find the expression that obey the same relation that makes f circ, and f star having the same relations that those three have and that we saw in the graphs, okay? So in the paper, using the equation, but don't bother about the equations, we manage to, given the coefficients of f, we can find the expressions for f circ and f star. The proof is in the paper. But let's manipulate that a little bit early. But before that, I want to propose something radical here. Let's reform the calendar, okay? Okay, we don't have the power of a Roman dictator, of a pope, but we are going to somehow reform the calendar. That's what Christian Zeller did in 1882. He introduced the so-called computational calendar. Okay? It's not a calendar used by any country, but it's a much more mathematically convenient calendar. So we can use that in our algorithms. Temporarily use the calendar, and then we map later to the official Gregorian/Julian calendar. So let me picture here two consecutive years, y and y plus 1, in the Gregorian/Julian calendar. as usual. These 2 years are split in 12 months, numbered as usual, from 1 to 12. So I'm going to contrast these years and these months with the corresponding in the computational calendar. So first and foremost, Christian Zeller fixed the De Chambers mistake. And he moved February to be last of the year. So the years are a bit shifted to put February at the end. So the years run from March to February. From March to December, he kept the number of months as usual, from 3 to 12. But now January must follow December of the same year, and February must follow January of the same year. So they get the numbers 13 and 14. That's the computational calendar. And there is a last thing, in the computational calendar, days are zero base. So the first day of the month is 0, not 1. And with that in mind, it's really simple to figure out that formula to map from the computational calendar, these are variables on the computational calendar, to map that to the Gregorian/Julian calendar. You might not have notes, but my code that I showed beginning, the very last block was doing this. The first 3 blocks were working on the computational calendar, and the very last block was mapping the date to the Gregorian calendar. Okay? Now, notice February. Notice the year that February falls on. It's off by 1 in the computational calendar with respect to the Julian/Gregorian calendar. And that's why exactly the issue we had before when we tried to figure out the formula for Y star in the Julian calendar. Actually, what we found there was Y star for the computational calendar. Okay? So it was, it's brilliant. Christian Zeller, thank you very much. Brilliant idea. So let's now see, okay, and I have to be precise here. I'm saying Gregorian/Julian and the computational calendar. Actually, there are 2 computational calendars, okay? One that is based in the Julian calendar, and the leap year rule for the computational calendar based on the Julian is off by 1 with respect to the Julian. And the same thing happens for the Gregorian calendar, the computational calendar based on the Gregorian calendar. So let's go back to Y star that we saw for the, we thought was the computational, the Julian calendar, but was actually the computational based Julian calendar. So the leap year rule now is exactly that, so this formula is correct. I insist this formula is correct for the computational calendar, it was wrong for the Julian calendar. And if you use the results that we had for the Euclidean affine function, if I equate the coefficients with the generic form of the F star function, we can get the A equals to 4, D equals 1461, and B equals 3. And having these 3 coefficients, we can easily deduce the formulas for when, Y, and Y circ here. Okay? Let's try now the same thing for the computational calendar based on the Gregorian. The leap year rule is off by 1 with respect to the Gregorian. I state it here. And here is a reasonable attempt again. I multiply. So this counts the number of days before year Y. So I first approximation, I multiply Y by 365, and then I do the corrections. 1 day every 4 years minus 1 day every 100 years plus 1 day every 400 years. Bad news? This formula is correct, but it's not an Euclidean affine function. So our beautiful theoretical framework doesn't apply directly here. But nothing, not always lost. We can still use Euclidean affine function if you do one thing, which is introduce the century. Let's put the century, make it a first-class citizen in calendrical calculation. Many of the algorithms, they try to get direct to the year. And I'm saying here, no, let's get the century first. We are basically acknowledging Aloysius Ligio's idea that every 4th century should get an extra day. And then we introduce these leap year centuries, which is off by 1 with respect to the Gregorian leap year rule. It's not when the century is multiple of 4, but when C plus 1 is multiple of 4. Okay, and then I leave for you to deduce this here. It's very similar what I did before. So we count the number of days in a century, normal, common centuries, and we do a correction every 4th century. So that's the formula for C star. And again, equating coefficients, we get the formula for the century and for the day of the century. So what do we have so far? Step back. So for the computational calendar, based on the Gregorian rule, so suppose that any days have passed since March the 1st, year 0, which is the first day of the computational calendar. Then we just deduce these two formulas here, right? So century, we know. How do we get the year? Notice the NC is the number of days within the century. It never crosses a boundary, century boundary. And within a century, the Gregorian calendar and the Julian calendar, the leap year rules, they match. It's exactly the same. So the deduction that we did before for the Julian calendar also holds here, the same formulas. The only difference is now that Z is not the year, it's the year of the century. But if I have the century C and the year of the century Z, that's the year. The only thing that remains to be found are the month and the day. And again, it's just the same thing over and over again, like we do with times. So we start with M star, which counts the number of days before month end. I have a table here, but remember that March is the first month of the year. And as expected, February is the last month. It doesn't create any trouble for us. M star doesn't need to know if we are in a leap year or not. It just works. And again, so it might seem also very esoteric how I get that, but you can see that this thing here gives the formula for the month, and there is a Euclidean affine function, and again, just equating the coefficient, yes?
Does the sort of clever bit shifting method of finding out what, how many months are in, or how many days are in the month still hold with the... No, it doesn't. That is particular for the Gregorian calendar. It's orthogonal to that discussion for this algorithm. Okay? So, and then we have this formula here. We can discuss later how we can make it more earthy. It's not that esoteric. But then we have the coefficients for M star, same exercise, equating coefficients, blah, blah, blah. We have the formula for M that gives the month, and we have the formula of M star, M circ, that gives the day of the month, or simply day. That's it. We have a complete calendar algorithm here that has no loops and no branches. But I still don't like that. I see a lot of divisions, and I don't like that. We are going to do something about that, okay? But before, so just overview. So we get the century and the day of the century, and from that we get the year and the day of the year, and from that we get the month and the day, and then we map back to the Gregorian or Julian calendar, in that case Gregorian calendar, okay? That's a complete, and it's fast, it is fast, but it still bothers me, the divisions. But before we handle the divisions, I want you to realize that we have incidentally solved a fourth problem, which is this reciprocal algorithm for this one, okay? Which gives the number of days from epoch to a given date. So how can we calculate the number of days from epoch to the date in the computation, in the Gregorian calendar? So first step is the opposite of the other algorithm. So we map from the Gregorian to the computational. Now we are in the computational calendar. YMD are year, month, and day in the computational calendar. And if you remember, Y star was the number of days from epoch to the first of Y, first day of year Y. And M star was the number of days from the first of year to the first of month. And day, D, is the number of days from the beginning of month to the date. So N is the sum of these three numbers here. So here is and here are the formulas that we have deduced before. Remember, this one was correct, but was not an Euclidean affine function. But that's not a problem because we are not interested in getting Y here. We're just using y star. So we have y star, m star, we have the n is just the addition of the 3. But here again, yes?
Yeah, I'm confused. Why is not an affine function if you like combine the terms with the year?
That's a very good question. That's a very good question. Because I did before, right? I multiplied 365 plus y times y plus y by 4, and I did a simple calculation, 1461 divided by 4, that's it, and you believe me, that's not that easy, okay? And we can think that the same thing will apply here, and we'll get an Euclidean affine function. But that's not the case. One problem is the minus here, but it's not the only problem, okay? So in the paper, we show that the other calculations that I did, the simplifications, I'm not lying, they work. Not in here. There are some algebraic results, they don't match, and you have problems, and it's not an Euclidean affine function. But it's subtle. It's subtle. We might believe that this is, and at some point I believe, and then I did the calculation, the unit test fails. Why? Yes, it doesn't work. And then months later I come back, oh, no, but this is an Euclidean affine function. No, it's not. So it keeps bugging me, and at some point I say, okay, it's not. I'm convinced it's not. I have my lesson. But it's in the paper. It's in the paper. So, what's my issue with division? Division is the most complicated arithmetic operation amongst the four. And not just for me, not just for humans, also for the CPU. It takes far more cycles for performing a division than a multiplication or addition subtraction, okay? So, I'm not very good with mental calculations, but I have this trick. Every time I have to divide by 5, what I do is I multiply by 2 and then divide by 10, because divide by 10 is just moving the dot, right? And the CPU can do the same thing, but in binary, okay? And here is how the CPU can efficiently evaluate n by 5, more or less. What happens is we multiply by 2 to 34 divided by 5, and then we divide by 2 34. But this number here is not integer. That big number you see here is an approximation for that one. It's actually the result of that one rounded up. So the result of this rational division here is a bit higher than n divided by 5. But we are not working with rational division. We are working with integer division. And integer division for positive integers, it truncates down. So maybe the error that we make with that approximation that is up, when it's truncated down, maybe one compensates the other, and we get the right result. And that's exactly what happened, since it was proven by Granwood and Montgomery, not just for n divided by 5, but in general. They wrote a paper in 1994, and many compilers, all the major compilers, they apply this trick nowadays. So if you write that in your code, that's what the expression that the compiler will generate in the assembly to CPU to evaluate. Yes?
Why specifically 2 to the 34?
Good question, good question. It could be any number, right? But then that approximation here, the larger the number here, the more bits of the approximation correct, okay? So 34 is the minimum amount for this result here to work for n in this interval, the interval of 32 unsigned integers, okay? If you take 64 bits, it will be much higher here. It will be 67, something like that, okay? But the compiler has all the machinery to compile time to know what that number is, depending on the type. Yes?
For this to work, then multiplication should be done in 64 bits, right?
Yes, it is done in 64 bits and then shifted, yes.
But if the original n is 64 bits?
So there are instructions that you can multiply two 64 bits number, and then it gives a 128 bits result that is split in 2 registers. And then you manipulate these two registers, shift bits from one to the other to do the final one. But that's possible, and the compilers do all this machinery for you. You don't have to do that. But it only works when the compiler sees the divisor, okay? If it doesn't know the divisor, it's going to generate a div instruction. But if it sees the divisor, if it's optimizing compilers -0 or -02, then it will do that optimization for you, okay? So let's see what that brings to our code. Here is an expression that I took from some implementations that calculate M and D, okay, the month and the day. Not ours, ours is a bit different. This one is the good implementations that we also manage to beat, and we will see why. So basically they have the formula for M and the formula for D. Remember that D was calculated like M circ. And M circ by definition was the difference between NY and M star. That's what happened here. Okay, so as I said, when the compiler sees a division, it do the Granul de Montgomery trick. So these two divisions here, they are not really divisions in the assembly code. They are multiplications plus some cheap operations. And after the compiler does that operations, then we can see that the multiplication becomes the bottleneck. Let's put it like that. And the number of multiplication is like a proxy for the performance of this code. Okay, and here, after the compiler transformation, we have 4 multiplications. And also notice that D depends on M. So the CPU must finish the calculation of M before it can start the calculation. The first thing it does to calculate this is multiply M by something. So we need to know M. So the compiler cannot start the calculation of D, so there is a data dependency here. But as I said, we have an alternative for calculation for D, which is given by this formula here. Okay? And now we have 1 multiplication and 2 multiplication here after Granul de Montgomery transformation. Now we have just 3 multiplications. And M does not appear in the expression for D. So once N3 is obtained, the CPU can start the calculation of M and D in parallel. Except that I'm lying to you. Because that expression here, Granul de Montgomery, they don't say anything about optimizing modulus operation. So currently, what the compiler do is they replace that expression here with this one, which has another multiplication. So if I take this one here and put here, that gives a fair assessment of the operations the CPU is going to do. And again, we have 4 multiplications, and D depends on N. So we are not any better than we used to be, right? Not yet, because Lawrence and I, we generalize Granul de Montgomery results to Euclidean affine functions. And notice here, we have a power of 2 divisor. And for a power of 2 divisor, that's a bit shift, and that's a bitwise end. And I can do the bitwise end even without having the result for the division. I can start the calculation of the modulus before I finish the calculation of the quotient. And we have an extra division here, but for that division, we don't care about the modulus of that division. And for that reason, we are fine just applying Granul de Montgomery. But when we need both the quotient and the modulus, that trick here allows both to be starting parallel, okay? And in the particular case, so it's not just that formula that we did that generically, and then for the particular case of the month, we have this thing here, these 2 equations here, so we can apply that to our code. And that's what we come. So we have the multiplication here, and another one here after Granul de Montgomery. And that's it. We have 2 multiplications. And there is no more data dependency between D and M. And the CPU starts, if you put that, you take the assembly code, you put in the machine code analyzer, you're going to see in the timeline that the CPU starts the calculation of M and D at the same time. And it finishes in much fewer cycles than the original formula. So that's the final version. We apply these tricks here, okay? And then, again, computational calendar. That's our main problem, and I covered the 4 algorithms. But maybe you have noticed that I didn't apply our beautiful optimizations of Euclidean affine functions to the first block. And for the second block, I applied just half of it. And I explained, there are 2 reasons for that. One is ugly, let's put aside. The other one, in my opinion, not my employer's, my opinion, is beautiful. And it concerns these 2 lines here. Notice that any bit, I mean, I suppose there are some bit-twiddling funs here, otherwise it wouldn't be here. Okay, I'm a bit fan of bit-twiddling, so look at that. Notice first that NC is something divided by 4. Let's call this something R. And for P2, I'm interested in the expression inside the brackets. And I'm going to replace one into the other. So at some point, the CPU evaluates that expression. It has R, which is in a register, and then it's going to evaluate that expression. Let's think in binary. So I'm representing here the bits of R, and I'm highlighting the 2 rightmost bits. So when we divide R by 4, which is the first thing that we had to do here, we shift the bits of R 2 places to the right. And then we multiply that by 4. So we multiply by 4, which, again. So we multiply by 4, and then we shift back to the left, and we fill the gaps with 0. And then we had to add 3, which in binary is 1, 1. That addition has no carry. So the same result that we obtain here, we can obtain just with a bitwise OR with 3. Good news, the major compilers, they are able to figure that out by themselves. I didn't need to do anything for GCC, but not all compilers, okay? And why do I call that historical bit-twiddling? Because these 4 here, that multiplication by 4, we can pinpoint that comes from decision of Sosigenes that every 4th year should get an extra day. That decision was taken more than 2,000 years ago. That division by 4 came from the fact that Aloysio Lilius decided that every 4th century would need an extra day. A decision that was taken more than 4 centuries ago. That 3 here comes from the off by 1 error of the computational calendar with respect to 4. An idea in the computational calendar invented by Zeller more than 140 years ago. And put everything together is our modest contribution from just 2 years ago. Thank you very much. I will be glad to listen to your questions. But before that, I want to express my gratitude to these 6 people, including my wife, for her support, and for an anonymous referee when we submit the paper. So if you find the original paper in the archive, please don't read that. We submit that, and we had an anonymous referee that was very harsh on us, but he was completely right. We rewrote the paper, and I think it's much clearer and much more enjoyable now, and so I'm very grateful towards him as well. And thank you. Here's some reference, and if you have questions, please. Any question, comment?
Yeah, so I lost track a bit. The last formula, what exactly it computes?
That one here?
Yes.
Is a step. It's just a step. It appears by all the reasons I said. It appears here. So you have the 4nc plus 3, and nc something divided by 4. So during the calculations, that expression appears in the middle of the calculation. So the CPU at some point evaluates that expression. It's not very visible here in the code, so that's why I did all this thing here to illustrate how we get there, how we get this point where the CPU needs to calculate this expression. And the very lucky things, again, the heavens want to have that. The heavens are bit twiddlers. Okay? Any other question? No? So thank you very much. And I'll be around if you want to discuss and the other problem, the homework that I gave to you. Thank you.